Hello, 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 everybody, and welcome back. We're going to finish off the 2001 Cayley paper. That's the grade 10 multiple choice contest put out by the University of Waterloo. You can get all their contests by clicking the link in the description. We're going to finish off this paper with question number 25. The circle with center A has radius 3 and is tangent to both the positive x-axis and positive y-axis. So I hear circle and tangent, I start thinking, well, if I drop a radius, I'm going to get a right angle triangle. Okay. Also, the circle with center B has radius 1 and is tangent to both the positive x-axis and the circle with center A. So I'm thinking drop a radius from B to the x-axis, that's going to be perpendicular to the x-axis. And also, since A and B, the circles at A and B are tangent, I'm thinking I should probably connect their centers as well. This is just experience and instinct talking here, but it's the sort of thought process I have when I read this question. The line L is tangent to both circles, so again I'm thinking drop some radii, get some right angles going. The y-intercept of line L is, okay, so the y-intercept is sort of up here. It's basically determining the height of this big triangle formed by the x-axis, the y-axis, and L. So we might want to think of it as a triangle, or I doubt we're going to get an actual equation for the line L, although we certainly have enough information to give A and B some coordinates. So we might go that route. But let's draw our picture and see. I'm going to throw in those radii and see what comes to mind. All right. Now I'm going to probably want to use this picture a fair bit, so I'm actually going to skip a page just so I can look at my picture more. So I'll draw my circles first. That's actually not a bad circle there. A slightly smaller circle here at B. A, and then we have L here, which is tangent to the both of them. It doesn't quite look exactly like the picture. L was a little steeper, but that's okay. So let's pick some colors and drop some radii. So we have 3's here. So if we wanted to figure out the height of this guy, we definitely already have 3 going. So we have a nice little square worked out here. We're going to have another one right here. And I'm going to want to connect up the centers of A and B using their radii. So each of these is 1. And each of the green radii were 3. Okay. So another thing I'm noticing here is I have tangent lines meeting at a common point up here, and you have one down here, but we don't need it. But that tells me tangent lines intersecting at a common point, they have the same lengths from that point to the point of tangency. Same down here, they're not going to be the same lengths as the ones up above, but we still have common side lengths here. Okay, and these quadrilaterals in here, they look similar. So a length of 4, and then a 3 and a 1, a length of 4 and a 3 and a 1. I would suspect that these guys here are the same, but I don't know that yet, so I'm not going to actually add it in. I'll just fill in the picture again. Okay. So what to do? So what I want is 3 plus this length right here. If I could work out this length up to the point of intersection up here, I'd be all set. So the question is, well, let's give it a name. So we'll call this X, and since I may have to work it out, we'll call this one Y. Okay, so if I knew 3 plus X, I would be all set. So what is there to do here? So if I connect, let's get orange out here. So if I connect to our y-intercept up to A, I'm going to have side angle side. I'm going to have two congruent triangles right here. Same right here. Now it's a shame that these lines from the y-intercept to A to B to the x-intercept don't all line up. Although I think that'd be impossible. Because I'd like to involve this fact here that A and B to have this nice little tangent with a 3 and a 1 here. And I think what I'm going to do is, we'll keep orange out, I think I'm going to make a little rectangle here actually. So I can make a rectangle there, and I can make a rectangle here. So I'll get some right angles here and here. And when I do that, this length is going to be 1, this length is going to be 1, so that splits the length of 3 into a 2 and a 1. And this total length here is 4. I've got a 4 and a 2 and a right angle. That to me screams a 30, 60, 90 triangle. So 30 degrees, 60 degrees, and 90 degrees. And the side lengths there, these are common, this is a very common triangle that you should always sort of keep in mind. They have ratios of 2, 1, and root 3. So 30, 60, 90 triangle, you go 1, root 3, 2. And in particular, I have in my orange triangle, in the middle here, I have a 4, I have a 2, and I have a right angle. Which means that this one's going to have to be, using Pythagoras, 2 root 3, which means I have to have a 30 and a 60 here. Okay. So that's a nice little hidden 30, 60, 90 triangle. I suspect that's intentional, because almost always the 30, 60, 90 triangles are intentional. They do pop up from time to time. I would guess probably at a rate of maybe 1 question per year, maybe a little less, but it is a very popular Pythagorean right angle triangle, especially even because it's got a root 3 in there, so they're not integer side lengths. So if you told me, root beer, there's a question on this Waterloo contest, and it's got a right angle triangle, I would say, oh, Pythagorean triples, 3, 4, 5, 5, 12, 13, and you said, no, if they're not integer side lengths, I would say, oh, it's going to be a 30, 60, 90 triangle. That's almost always how it goes. 30, 60, 90 triangle is very important to keep in mind when you're doing these and other math contests. All right. So we've got that information. We also have these nice little rectangles here. And now we know this other side length of 2 root 3. So if I see one 30, 60, 90 triangle, I suspect there might be others. In fact, I suspect I might have a 30, 60, 90 triangle from A to the y-intercept, and that would make my life a lot easier, because then x would be 3 root 3 or something. So let's investigate that a little bit. I'm going to draw my picture a little bit bigger. I'm just going to draw the part that I need. That's awful. That's awful, and I feel ashamed of who I am as a person. Kind of look like a guy with a hat. We'll draw our circle first. That's also a terrible circle. One more try. One more try. All right, that's a little better. Okay. So we have our x here. And we also have these tangent lines here that have also got some angles here. So we have 2's here. But more importantly, with this 4 here, I know that this is going to be 60 degrees. This is going to be 60 degrees. And I already know I sort of have a square down here, side 3, so this is going to be 90 degrees. So if I had angle theta in here, theta is the full 360 degrees, minus 60 degrees, minus 60 degrees, minus 90 degrees. Please let this be something like 120 or 60. So that's 300 minus 150, so it's going to be 150 degrees. All right, let's double check 150 degrees plus 90 plus 60. Yeah, so it's 150 degrees. So if I drop this down here, I'm going to have each of these is 75 degrees. I've got this 3 here. Okay. Well, all is not entirely lost. What I'd like to do is I'd like to get an exact form here, but because we've got our answers are given to us in exact forms. So I don't want to use decimal approximations if I can help it, but I'd also like to take this opportunity to use this 75 that I just worked out. Because if I have a right angle triangle, and this is a grade 10 contest, so we can definitely use SOHCAHTOA. If I have the hypotenuse, if I have an angle here theta, this is the opposite side, this is the adjacent. The tangent of theta is going to be the opposite over adjacent. This is SOHCAHTOA. This is something that is commonly covered in grade 10 when you do trigonometry. Okay? So what I can do here is I can, we'll keep it in black. I can say, well, the tangent of 75 degrees is going to be x over 3. Or really, x is just 3 times the tangent of 75 degrees. And so we'll flip the page. What I want, if you'll recall, right here, we've got x plus 3 is the y-intercept. So that's 3 times the tangent of 75 degrees plus 3. Now we rearrange, we get x is 3 times tan of 75. But I don't know what tan of 75 is off the top of my head. And if I grab my calculator and do tan 75, it's not a number I recognize. I got 3.732050808. Now that looks a little like 2 plus the square root of 3. And oh my gosh, is it? So it is the square root of 3. Okay. So if you're keen and you remember things like that, then tan 75 is apparently, we just go back here, tan 75 is apparently 2 plus root 3. Okay? But suppose we didn't know that. We're doing a multiple choice contest, which means they gave us possible answers. 5 possible answers. There's no reason not to go through them and see if the decimals are going to work out and be similar to the decimal expansion of this thing. So we grab our calculator. We don't know what tan 75 is, and when we look at it, we don't recognize it. Tan 75 times 3 plus 3, it's about 14.19615,242. Okay? So this is the 3 tan 75 plus 3 is an exact answer. So when we compute each of those 5 possible answers, they need to be exactly this. So answer A was 3 plus 6 root 3. B is 10 plus 3 root 2. So we've got 3 plus 6 root 3 and 10 plus 3 root 2. What we're going to do is we're just going to plug them in on our calculator and decimal expand them out. 8 root 3 and 10 plus 2 root 3. So it's entirely possible that some of these were chosen so they'd have a similar expansion to this but not be the right answer. So it might be that 2 of these worked out to be 14.196 on a calculator. And what was E? 9 plus 3 root 3. Okay. So let's get to working these out. We'll start it with A, so 3 plus 6 times square root of 3. So that looks like 13.3923048. Not really good. It should be the exact same decimal expansion because these are exact answers. So 10 plus 3 root 2. We got 14.24264 something or other. Close, but no cigar. We're looking for 14.19. How about 8 times root 3? Well, again, we've got a 13 point something. Doesn't really matter. How about 10 plus 2 times root 3? Well, we've got a 13.46410. So unless we've made a huge mistake, it should be E, but let's double check by expanding it out. 9 plus 3 times the square root of 3. And we get 14.19615.242. We have the exact answer that we want. So that's the match exactly. We don't need to work out any more of the triangle. We don't need to do any other work with angles or even adding in coordinates, doing any of that stuff. We got some number that we could plug in our calculator, and we're abusing both the fact that we can use a calculator on this contest and also the fact that it's multiple choice. So we only have 5 answers to check. If this were the written contest like the Euclid, this would not work because we don't have a multiple choice thing here. Okay, but we're exploiting the fact that it's a multiple choice contest, and that allows us to maybe save us some time every once in a while, like this. So we just plug these numbers into a calculator, and suddenly we work out the answer is E. Clearly we have E, and that rather nicely wraps up question number 25, and so finishes off the 2001 Cayley contest. As usual, thank you guys so much for watching. I enjoyed this particular Cayley contest. Feel free to throw a like on this video or some of the other ones if you liked particular questions in this year. And so that's Cayley. So we're going to move on to the 2001 Fermat in the next set of videos. And I'll be hard at work at the 2002 Cayley if that's one you're particularly preparing for. And that'll come out in the future as well. So thank you guys for watching. And as always, I'll see you next time, whenever that is.